law. Hooky, 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 hooky law.
For the last section in this chapter, let's work with an actual real data set called the lung volume data set. And this is a well-known data set in the medical field. We have in this data set FEV, which stands for the forced expiratory volume. In other words, this is how much you blow. And we should edit that. Okay, we are going to ignore the age column, and we're going to try to use height, and we also have some categorical variables. The question is, if I can tell how tall you are, does that tell me what your forced expiratory volume should be, which we are definitely not going to say is how much you blow. So let's take a look at how this volume is predicted by your height, and we're going to color it based on gender. Hang on, data equals lungs. So you can see curvature. Does it look like males and females are different? Hard to tell in this. Now, this has huge medical implications. So if there's even a tiny bit of difference between males and females, we want to be able to use that. We can also try to look at, does it depend on whether you're a smoker? Okay, maybe, right? See how the reds are up here, but the blacks seem to have a little bit of a different curve? I don't know, though. Yeah, it's going to be a close call. Well, let's try it and see what we get. I'm going to start by doing a quadratic model on this. Now, if you read the papers, they've talked about using logs, and we're going to spend an entire chapter on that because logs are a very important function. But for right now, let's stick with just a polynomial, and we'll see if we can get good results, even though a log probably would give us some better ones. We're going to do FEV based on height plus, let's start with just height squared, and I'm going to add in some categorical variables later. Data equals lungs. First thing I want to do is look at those residuals. I'm going to blow them up big size instead of putting 2 by 2. Okay, I see some non-constant variance maybe. In the middle it's alright, but towards the end's not so great. There seems to be some swerve when you look at it from this side. None of the data points in particular are bad leverage points. So a few things that cause me some concern. Maybe we can improve this, but overall not terrible. And as you would have expected, the height squared term is significant, which isn't surprising because we saw the curve in the original plot. So now let's include one of those categorical variables, in this case gender, which, oh yay, that's called sex. Let's see if I can record a video and avoid using that word in every other sentence. Now I'm going to multiply my height times the categorical variable, plus I need height squared to also be multiplied times sex. So our data set is called lungs. There's our fit. Do we have better residuals? This is going to be very telling as to whether it's actually a helpful variable. I don't see a lot of difference here. Boy, it looks like maybe it's following the curve just a little bit further. Still curve here, and this one still looks good. So I don't see a whole lot of change here. And in the summary, there is where the effect of, okay, so there definitely is an effect based on sex, and okay, even timesing it by height and height squared, both of those are significant. It was hard to tell in the picture, but the p-value says the data definitely shows that sex does matter. That's the weirdest sentence ever. Okay, so we found out one categorical variable matters. How do we add in another categorical variable? So I'm going to steal this. What do? Well, if we want to have an effect of smoking on height and smoking across the different genders on height, I can do smoking right here, and I think I spelled it right. I think it's capitalized smoking. All right, what happens here? We get an error because smoking is not found. Really, what's it called? Smoker. Now think about the implication here. How many categories do we have? We have 2 genders and 2 smoker, non-smoker. There's actually 4 categories going on here. Have I improved my residuals? I don't see a lot of difference there. And this is still looking about the same. Some of this would have been fixed if we were doing logs, which we're not. That looks about the same. Ooh, and now there's a data point that this data point 191 did not look weird before, but now suddenly there's something about 191 that looks weird. And I actually don't know what it is. I probably should pause the video to go look at data point 191. This is a male who does smoke and has a lung volume of 1.953. How does that look in regards to the picture? Okay, that's very low. 1.93 is very low. It's a male. How tall was this male? 58 was the height. So here, so this male should have had more lung volume. Something's wrong with this particular person's lungs that when they did the blow test, it didn't go so well for them. Can I tell why? I don't know, and I don't see anything here telling me that this is an error. There's no error code or, you know, 0.99999, which would make me think that somebody was just typing in numbers. I think this is a genuine data point and that we genuinely have a person who was lower than they probably should have been. Wait a minute. The age is 9. Are we talking about a 9-year-old smoker? Ken? Okay. Apparently I was wrong about what this data set was. These aren't smokers. These are whether they're in a smoker's house. So this is a 9-year-old whose parent smokes, which makes this data set much more interesting. Now we're talking about the debate of secondhand smoke, and we're talking about kids and our kids in danger, which really adds a little bit of excitement to this. So let's see whether it matters if you're a smoker or not. And hang on, let's size out plot. This is why I hate having to hit return after every single plot. Look at those p-values. See how they're big? Now, interestingly enough, you'll probably notice a couple of things. All the p-values are big, where they weren't before. Having an extra variable in can sometimes mess up other variables, and that's why later we're going to have a whole chapter on multicollinearity. How do you recognize this problem? How do you deal with it? For right now, it's clear that marking whether they live in a smoker's household or not, according to this data set, did not help. Now, it did matter the effect of gender. So it makes me curious, if I had smoking but not gender, would that matter? So here's that same fit with smoker instead of sex, and I just want to look at the p-values real quick. P-values are big. Having smoker in the model really is not helping. So if we want to predict these children's lung volume, knowing whether their parents smoke or not isn't being helpful, at least not with this data set. So I'm going to go back to the model before where we just had gender, and we already looked at the residuals, they looked good, and some of these p-values are significant. Now, which ones are not? We have height squared was not significant, but male times height squared was. And here we have height is not significant, but male times height was. And this leads us into the classical debate. If two variables times each other are significant, but one of those variables is not, do you include it or do you not? And I'm okay with whichever way you decide to go. I'm going to choose to leave it in, which is probably the more common choice among statisticians, but you can go the other way if you want. So I'm ready to call this my final model. If we want to predict children's lung volume, we're going to do it based on their gender because it matters, and it's going to be quadratic based on their height. So let's draw us the picture. The first thing I'm going to want to do is to make a bunch of height values that I can use for my prediction, hence the hat. And then for males, who's my baseline? My baseline's obviously female, right? So FEV female, let's start with them because the baseline's going to be easier. And that's going to be 0.1425 times height hat. Is that all? No, because we have a height squared. So minus 0.0002566. I hope you're following along with where I'm getting these letters. Height hat squared. Here was height squared. Since we're talking about baseline, that's the effect that I need. For males, it's going to be the same thing we had before, except I need to add a male effect to each of these. So I'm going to go plus something here, and I want the negative to be part of that number, so I'm going to go plus something there. Okay, what do I add for the intercept? For males, it's that 13.92. And when I talk about heights for males, height for male, it's this minus height male. 0.48347, that should be enough decimals. And height squared for males is this number right here, 0.004178. So now I have both of these. I can add them to my picture. And if this doesn't work, we're gonna pause the video. It does, oh, it's gonna, because I have to run the line. Height hat not found. Please. Okay, good. Now, interestingly, this black line is also curved because it comes with this height hat squared right here, but that curvature is very subtle and slight so that it really does almost look linear right here. And that's why those terms for the height squared and height were not being significant, because it looks linear here according to the female. But let's go ahead and grab these two prediction equations, and I'm going to try to explain the effects as well as grabbing that plot. Okay, how would I explain this to a client? First off, I'm going to mention that we couldn't show that whether the parents smoke was affecting their FEV for their lung capacity. Now, that doesn't mean it's not true. It means this data set wasn't what could show it. And that's a hotly debated topic with a lot of data sets out there trying to see what the effect is and whether it's provable. And I'm going to put in the prediction equations, which, since I have the code, it's going to be partly easy, but I want to make it look nice. Which for the females is pretty easy, but for the males, I'm going to have to do a little bit of math here. Now, it's interesting for this data set, the females' intercept was negative, males was positive, and then here positive, and for the males it was negative. I mean, it's switching signs. It's confusing to look at these and to try to figure out what the difference is between the males and females, which is why a picture like this is worth so much. And now all I need to do is try to describe, what do I see here? And I'm sitting here trying to figure out which one's male, which one's female. I forgot my legend. Fortunately, that's fixable, and I can replace this with something that has a legend so I can tell. Okay, for the males, it looks like on the lower region they're higher, and on the upper region they're higher. I was about to say it's always higher, but that's not really true, is it? That's hard to see. Can I go back to this plot and turn off the color of the dots? Yep. See, males bend slightly lower than females. Oh, but that's such a slight thing. Is that really that importantly bigger? Okay, well, I'm going to have to try to make some decisions. Do I mention that? Here's what I'm going to do. I'm going to mention that usually males are higher, and here it's practically about the same, right? Statistically, they might be different, but in practicality, those are about the same. So, in the smaller and taller heights, the male FEV is quite a bit higher. And then I'm going to try to mention that curvature. For the females, there's not much curvature there. For males, the curvature means their FEV is increasing more dramatically as they get taller. And I sat here with the video paused for a while trying to think, why might this be happening? The only idea I could come up with is testosterone, because as males grow taller, there's also a dramatic increase in testosterone, so maybe there's a link there. And if I was the client, I'd be like, oh, that's interesting, I want to think about that. Should we do some experiments or studies? Pretend I said studies. Experiments does not sound like a good thing. But I just want to show the client, and really it's important that you show me as the teacher, that you're really thinking about the implications. What does it mean and why? So just another example of a quadratic data set. In this case, it really could use some logs, but we haven't gotten into logs yet. But I hope by this point you're saying, I can handle squaring. I need to use that indicator function in R with that capital I, and I need to make sure that if I have categories, I'm multiplying them by each of these quadratics. But then I draw a picture and I just explain what I'm seeing and try to think about why, and the client could follow something that's fairly complicated. This quadratic is not an easy thing, and they'll be able to understand it. Let's move on to some of the homeworks, and when you're ready, we'll be ready to tackle on numerical by numerical interactions.